Hello guys, this is Dev. Today we are going to learn about moment of inertia and its calculation for different materials. Okay. So what is moment of inertia? Well, you see, a simple definition I will tell. For example, if this is the axis, okay, and I have to calculate moment of inertia of a mass m from this axis, and the mass m it has a is at a distance r from the axis of y. So moment of inertia from axis of y called iy will be equal to m times square of the distance from the axis. Okay, if suppose this distance was suppose a and this is x axis, then moment of inertia from x axis would be equal to ma square. Okay, it will ix will not be equal to mr square. This is wrong. Okay, the distance from the axis is always noted in the case of moment of inertia. Okay, this is for a single mass m. All right, so for a single mass we knew. Now if I take moment of inertia for an extended body, say like this, and I take an axis somewhat here at point o. Now I want to find out the moment of inertia of body from point o. So we will take small masses. Okay, so this can be m1, this can be m2, alright, this can be m3. So the moment of inertia of mass m1, which is at a distance r1 from o, this will be equal to di. Okay, because moment of inertia will be an infinitesimal, because mass is infinitesimal. Okay, for example, di will be equal to dm times r square, and for m1 it will be m1 r1 square. Okay, for m2 we will add m2 r2 square, for m3 it will be m3 r3 square dot something like this. Okay, so in nutshell I would be equal to summation mi ri square. All right, summation of mi ri square, and I will go from 1 to n. Okay, so this is for an extended discrete body. All right, this is for an extended discrete body. If I just apply calculus over here for a continuous extended body, all right, so this summation will change to integration, mass will be infinitesimal, and this will be di, this will be integrated, and this will yield I, and this will be r square. So this will be the moment of inertia for an extended continuous body. Okay, now let us take one example. And always remember, moment of inertia is always calculated from an axis. Okay, if there is no axis, it will be very difficult. So for example, if I take a rod, this rod is of length L, all right, and I want to calculate moment of inertia of the rod from the axis passing through its end point. And suppose this axis is y, I want to calculate Iy. What is Iy? How much is Iy? Okay, so you see, rod is continuous. This rod is continuous, just remember this. So we will apply calculus over here. Okay, so I will just assume a small mass of length dx, say, and at a distance x from the axis. Okay, what will be this small mass? Since the length is only a factor which is constant, okay, length L is constant for rod, so we can take mass in terms of L. Okay, terms of L. So we have dm. This dm is the mass of this slight strip which is of width dx. This will be equal to m divided by L times dx. So dimensionally this will be mass only, because this is length and this is length. The dimensions can get cancelled, and the dimensionally dm will be equal to mass only. All right. So what will be the moment of inertia of this thin mass which is at a distance x from Iy? This will be equal to Iy will be equal to, we can write this as diy, as mass is infinitesimal, so the moment of inertia of this mass will be infinitesimal. So this will be equal to dm times x square, since the mass dm is at a distance x from the axis. So we will just integrate this. What will be dm? Dm was m divided by L dx, okay, and this is times x square. We will just integrate this. So from where will the integration go? You see, since mass is at an end of the rod, we can assume the end of the rod as origin O, and we can assume the coordinates of the end of the rod as origin. So from origin it will go to length L, and this will go from 0 to I. Alright. So diy would be equal to integration 0 to L m divided by L x square dx. Alright. This will be 0 to iy. This will be iy equal to m divided by L times this integration x cube by 3, and we will apply limits over here. So we will get ml square by 3. Alright. So moment of inertia of rod from end is ml square by 3. Alright. This is the moment of inertia of rod from the end. Now I want to find out the moment of inertia from the center. Say if I take a rod and if I take this axis which passes through the center of the rod. Now what will be the moment of inertia of the rod from the center of the point from which axis is passing? So again we will have to assume one strip of mass dm, okay. This, let's say this is a strip of mass dm and this axis is origin, let's say. Alright. So as I already told you earlier, dm would be equal to m by L times dx. This is x and this is dx. Alright. So what will be di? Di will be equal to dm times x square, and di will be equal to m by L dx into x square. What will be the limits now? You see, the limits will be changed because, you know, if I am taking a strip of mass dx over here, similar strip I will have to take here also, because the rod is not half, the rod is full. So similar distance would have to be calculated x, and this would be dx also. But you see, the limit of this mass will go from minus L to L. Alright, since mass is whole, we will have to take first the left hand side and then the right end. Alright, so this will go from minus L to L, and this will go from 0 to I. Since I am assuming the standard moment of inertia of reference will be 0, so I would be equal to m divided by L x cube by 3. This will be equal to minus L from minus L, sorry, actually this is minus L by 2, yeah. Since this is the origin, this will be half of L and this will be half of L. So total would be equal to L now, yeah. This will be minus L by 2 to L by 2, alright. This will be like this, right. So I would be equal to m by L. We can take L cube as common. We can take L cube as common, and 1 by 3 we will also take common. Since x cube, this will be 1 by 8 plus 1 by 8, because cube of minus half will be minus, and we will always we will subtract it. So this will be 1 by 8 plus 1 by 8. This will be equal to m L square by 12. So this is the answer, okay. So moment of inertia of rod from center is ml square by 12. Alright. So now we arrive at a very important theory from this. This is called theory of parallel axis, okay. Theory of parallel axis. What is this theory? You see, when I took a rod, I have calculated the moment of inertia from the center. Yes, I have calculated the moment of inertia from the end. Let us say this is IA and IB. Alright. There is a solid relation between IA and IB. Alright. So what is it? For example, this is for, let's say this is length L by 2 obviously, and this will be L by 2. So how it goes by this this way. For example, IB plus M times L square by 4 would be equal to IA. M into L by 2 whole square. Alright. This is the theory of parallel axis. So what was IB? IB was ml square by 12 plus ml square by 4. Okay. So I just take the LCM. This will be 12. This will be 1 plus 3 and times ml square. So this is 4. This cancel out and this will result in ml square by 3, which was IA. Alright. So this is theory of parallel axis and moment of inertia. If the axes are parallel and separated by a distance, then one axis can be calculated in terms of other if we add mass times the distance square. Alright. So IB plus m times L by 2 whole square. This will result in IA. Alright. This is the moment of inertia along A axis. Axis at the end. Sorry. Alright. So let us calculate the moment of inertia, say, for a ring. I want to calculate a moment of inertia for a ring. This is a ring and the axis passes through the center. So what will be the moment of inertia? If I take a strip of mass, this strip has length ds, and you see in a ring, length is always constant. Since length would be 2 pi r, this will always remain constant. This is the radius. So we can express the mass in terms of length. Alright. So dm would be equal to dm would be equal to the whole mass divided by the total length times the length of mass, ds. Say ds makes an angle. This angle is d theta. Alright. So in circular motion, I already told you ds was r d theta. Okay. So we just put the value of ds over here. We have dm equal to m divided by 2 pi r times r d theta. Okay. R gets cancelled. So we have m divided by 2 pi times d theta. Alright. So this is dm. Now I want to calculate the moment of infinitesimal moment of inertia, which is di of the dm. This will be, since dm is at a distance r. Alright. Since this is the ring and this mass is at a distance r from the center. Okay, this is very thin. This is very thin width. Okay, don't consider it very wide. This is very thin. This can be neglected. Okay, since this is at a distance r, so the moment of inertia along the axis for dm would be equal to dm times r square. Alright. Yes, the moment of inertia for this would be dm times r square. Alright. So now di would be equal to, what was dm? M by 2 pi r square times d theta, right? So di was m by 2 pi r square times d theta. Now we will integrate this. You see, I am integrating. How can I integrate? Because of symmetry. Mass, we can take any infinitesimal mass, it will make an angle, and this will, the infinitesimal moment of inertia will be this. So they can be added up. Alright. So this will go from 0 to 2 pi. If I consider this as 0, this will go for the whole ring for 0 to 2 pi. Alright. So I would be equal to m by 2 pi r square. Alright. M by 2 pi r square times d theta, and we will integrate this d theta from 0 to 2 pi. So m by 2 pi r square times 2 pi, this will cancel out. So I for ring would be equal to mr square. Okay. So I for ring would be mr square, where axis passes through center of ring. Okay. Just remember, without axis everything is fail. You will have to see the axis. Don't get confused. If this axis pass through this end, the moment of inertia will not be mr square. Alright, it cannot be mr square. For this, if say this is ia, this ia will not be equal to mr square. This is io, this is equal to mr square. Alright, this will not be equal to mr square. Okay, so now we calculate moment of inertia for a disk. Okay, you see, disk is different from a ring because ring had its mass along the length. Alright, this space was hollow and here was the mass, but this is not the case for a disk. Disk is not hollow. Disk has mass everywhere. Okay, and for a disk of radius r, since mass is distributed along the area, So we will take mass in terms of area. Okay. So what is area? Area is pi r square. Here we took mass in terms of length because mass was distributed along the length. Inside there was hollow. This is ring and this is disk. Okay. Here mass was taken in term of length. Okay. So for a disk, we will assume mass in terms of area. Okay. Now, say this is a disk and this has a radius r. Now I want to find out the moment of inertia of this disk. So what I do is I divide the disk into thin rings. Okay. For example, this is one thin ring and similarly subsequently other thin rings. Say this ring has an area of radius r. Say the ring has a radius r, and now I will describe the mass of the ring in terms of the area of the disk. Okay. So let's say the mass of the ring is dm, and let us assume the whole mass of disk to be m. So m divided by pi r square. This was a constant quantity as mass is constant and area is constant, and we can express this dm in terms of area of ring. So what this will be, since ring and also ring has a width of dr. Okay. So ring is at a distance of r from O and has a width dr. So what will its area be? So its area will be 2 pi r, which is the length of the ring, times the width of the ring, dr. This will be the mass of the ring. Since I already told you mass can be taken in terms of a constant quantity, and this can be either length or area. Okay. So constant quantity in terms of length will be m divided by the whole length, but in case of area this will be m divided by the whole area. So here this is m divided by the whole area times the differential area, which will be 2 pi r, which is the length of ring, times the width of the ring. Okay. So dm would be equal to m divided by pi r square times 2 pi r dr. So now I want to calculate the moment of inertia from an axis passing through O. Okay, let us assume this to be z axis. So first I will have to calculate moment of inertia of this thin ring. Let us assume the moment of inertia of the ring to be di. So what will the moment of inertia of the ring be from the z axis? This will be dm times r square. Alright, r is the distance of the ring from the z axis. So di would be equal to, what was dm? M divided by pi r square times 2 pi r dr times r square. Okay. And this will be integrated from 0 to I, and this will be integrated from 0 to r. Okay. Capital R, because we are taking the whole disk. Alright. So pi gets cancelled over here, and this expression will be then I equals m by r square, twice m by r square, integration r cube dr. This will go from 0 to r, and this becomes 2m by r square. Putting the limits, we have r4 by 4. R square gets cancelled, and we have 2 and 4 gets cancelled out, so we have m r square by 2. This is the answer. Okay. This is the moment of inertia of a disk with axis passing through the center. Okay, vertical axis passing through the center along the z axis. Alright. Now I want to find out the moment of inertia of a cylinder. Okay. I want to find out the moment of inertia of solid cylinder, which is uniform. Alright. So let us consider a cylinder. Say this is a cylinder and this is a solid cylinder. Alright. Solid means the inside space is not hollow, inside is filled, and mass will be expressed now in terms of volume. Okay. Mass will be expressed in terms of volume, because volume is a constant quantity and mass is distributed along the volume in this cylinder. Let us say this cylinder to be of radius r. So mass will be expressed in the form of volume. So what we do now is we take thin cylinders. Okay, let us take thin cylinders, and thin cylinders have radius small r and width. Okay, these thin cylinders have width dr. This width is dr. Okay, so now you see mass divided by pi r square, and let us take the length of the cylinder to be L. This will be a constant quantity. Okay, as I already told you, dm can be expressed in lambda dx or dA or dV. In terms of dx we take lambda. Okay, in terms of dA we can take sigma dA. Okay, sigma is the density. These quantities are always constant. Okay, and in terms of volume we can take the density of volume. This is the areal density sigma and this is the volume density rho. Okay, so this is rho. So what will be the mass of cylinder? What will be the mass of cylinder? So, and mass of this thin cylinder, let us assume the mass of this thin cylinder to be dm. This will be rho times dV. dV is the volume of this thin cylinder. So what is the volume of this thin cylinder? You see, let me draw it over here. You see, this was the cylinder. Okay, now I want to calculate the volume of this thin cylinder. Since this is very thin cylinder, I have assumed inside this will be negligible and only this much portion will carry the volume. Okay, alright. So if this is R and this is dr, so what is the volume inside, not of the whole, but I want to find out the volume of the difference, because the mass lies inside between the two. Okay, and let us suppose this to be L. Alright, the length of cylinder. So this would be pi r plus dr whole square times L minus pi r square L. Okay, this is the differential volume of the cylinder. Okay, so we can take pi L as common, r square plus dr whole square plus 2r dr minus r square. This gets cancelled out. Okay, now dr is very small, you know, infinitesimal. Since dr is infinitesimal, dr square will be very small than dr, so we can neglect this and this can approach to 0. Alright, so the differential volume of this cylinder would be equal to 2 pi r dr times L. Okay, this is the differential volume. So now I have to calculate moment of inertia of this cylinder passing through the center, axis passing through the center, and this is the bigger cylinder. Okay, this bigger cylinder has length L. Length of the both the cylinders are equal. Okay, so di would be equal to dm times r square, because the mass, the differential cylinder is at a distance r from the z axis. Okay, so what will be di? dm was m divided by pi r square L times 2 pi r dr L times r square. Okay, this will go from 0 to I and this will go from 0 to capital R, because we are taking it for the whole cylinder. This is R. Okay, so now L gets cancelled out, pi gets cancelled out. Okay, I would be equal to 2m by r square, 2m by r square times r cube dr, and this will go from 0 to r. Okay, so I would be equal to 2m by r square integration of r cube dr. This will go from 0 to r, so I would be equal to 2m by r square r4 by 4. These gets cancelled, this will be r square and this will get cancelled, this will be 2, so it will be m r square by 2. Alright, so now we have the moment of inertia for cylinder. okay, passing through with axis passing through its symmetry is mr square by 2. This is the answer. Alright. Now let us calculate moment of inertia for solid cone. Okay. Suppose this is a cone, this is a point O, this is point A, this is Z axis. I want to calculate the moment of inertia of the whole cone from an axis passing through Z. Okay. So I assume a disk. Okay. This is a disk. This is a disk and this has a radius small r and a width dx. Okay. Now the only constant quantity in this cone is volume and mass. Okay. Volume of cone is 1 by 3 pi r square times h and mass is m. So I can take a density of cone as constant, m divided by 1 by 3, this will be 3m by pi r square h. Alright. So I want to calculate the mass of this small disk. So what will be the mass of this small disk? dm would be equal to rho times dv. dv will be equal to the elemental volume of the disk. What is the volume of the disk now? You see, volume of the disk would be the area of disk times the width of disk. Okay, so elemental volume of disk would be area of disk is pi r square and width of disk is dx. Alright, this is the volume of disk. Now let us consider this point as B and this as C and D. You see, triangle ACD is similar to triangle AOB. Alright, when these two triangles are similar, okay, when these two triangles are similar, since these are parallel lines and you see this angle 90 and this angle 90 are same. In ACD, angle CAD and triangle AOB, angle OAB is also same. Alright, since both these angles are same, the last angles have to be same. So angle we can say. Okay, so since these two triangles are similar, we can apply similarity of congruency of triangle here. So we have r divided by capital R would be equal to x divided by h, since the disk is at a distance x from A. Okay, this can be applied. So what is the mass? dm would be equal to 3m divided by pi r square h times dv. dv would be equal to pi r square times dx. Okay, alright. So now what is r? r from here would be equal to rx by h. Alright, yep, r would be equal to rx by h. So dm would be equal to 3m divided by pi r square h times pi r square dx, right? And r was rx by h. Alright, so we just substitute the value of r over here. We have pi r square h times pi r square by h square times x square dx. Okay, this is the elemental mass. Alright, let me draw the figure again. This was the cone and this is the elemental disk. This is the width dx at a distance x. This is r, this is small r. Okay, this is A, this is O, this is B, this is C, D, and this is height. Now you see, this is a disk and I want to calculate the moment of inertia of this small disk by via the axis z passing through its center. As I have already told you, the moment of inertia of disk passing through its center was half mr square. Okay, so what is the moment of inertia for this elemental disk? This will be half dm r square. Okay, so this would be the moment of inertia of this elemental disk, half times dm r square. Sorry, this is small r. Okay, so di would be equal to half dm times small r square. Okay, now let's calculate. Di would be equal to, what was dm? We add half over s, so it becomes 2 pi r square s times pi r square by h square. What was r? X square dx times r square. We have to also write r square. What was r? R was rx by h, right? R square x square by h square. Okay. So r square gets cancelled out. Alright. Di becomes 3 and also pi will get cancelled out. 3 by 2 h, and this is m, and h square h4 and 1h would be equal to h5, and this would be equal to r square times x to the power 4 dx. Yeah. Okay. This is the elemental moment of inertia. 3m r square by 2h to the power 5 times x4 dx. Now we will just have to integrate this, and you see during integration x will grow from 0 to whole h. Okay, since we are taking the cone and this is x, the disk is at a distance x from the point A. Okay, so di would be equal to 3m r square by 2h to the power 5 times x4 dx. We just integrate this. This will be 0 to h and this will be 0 to I. So I would be equal to 3m r square by 2h to the power 5 times x5 by 5. This will be 0 to h. I would be equal to 3 by 2 m r square by h5 times h5 by 5. This will cancel out. So I is 3 divided by 10 m r square. This is the moment of inertia for cone. Okay, 3 divided by 10 m r square. Now we move on to the next problem. Suppose we have a hollow sphere and I want to calculate moment of inertia for a hollow sphere about this axis passing through the center. So how do we do it? You see, since this is a hollow sphere, I know the inside space of this sphere would be empty. Okay, since it is empty, we can assume the sphere to be concentrated only at its boundary, and we can assume the sphere to be made up of small differential rings. For example, I assume this ring. Okay, numerous types of these rings are drawn from this sphere, and accumulation of these can make the whole sphere. Okay, so I am assuming just a thin ring. Okay, and this ring, the edge of this ring has a radius r with respect to O and makes an angle theta with respect to O. Okay, also you see the ring has some width. It is a very slight width, and the next end of the ring is also at a distance r because it is at the edge, but the angle here, let us suppose it is d theta. Okay, now I want to find out the mass of this ring. So how do we do it? You see, the area of the sphere, surface area, would be equal to 4 pi r square. This would be constant. We will not take the volume. Okay, we will not take the volume as sphere is empty, as sphere is hollow, we can also say. So we will not take the volume, we will only take the surface area of the sphere. Okay, surface area is constant 4 pi r square, so we can express the mass of the ring in terms of surface area, as I already earlier told you. So let us suppose this distance to be x from the axis x. Okay, now I am just drawing this figure here. This is the center O, this is R, alright, and this is the inner side of the ring, and this is x. Sorry, this is x. Okay, and this is the width of the ring. Okay, now this is also r. So what is sine theta over here? Sine theta would be equal to perpendicular, which is x, divided by hypotenuse, which is r, right? So x divided by r. So x would be equal to r sine theta. From here we can get this. Okay, now what would be the differential length of the ring? This elemental length, actually the center is making an angle d theta with respect to this elemental length. Suppose this is ds and this is an arc, say, and this is d theta, As I already told you in my previous videos, ds is equal to r d theta, right, for an arc. So we have ds and we have x. Now I want to calculate the area of the ring. What will be the area of the ring? The area of the ring will be length of the ring times the width of the ring. Okay, what is the length of the ring? 2 pi x, since ring has a radius x, times the differential length, which is ds. Okay, this will be the area of the ring. All right, so now the differential area of the ring would be equal to 2 pi x ds. What was x? X was r sine theta and ds was r d theta. All right, so this is the differential length, differential area of the ring. Okay, so this is 2 pi r square sine theta d theta. This is dA. Now I want to find out the differential mass. Differential mass would be expressed in the surface area, in terms of surface area of the ring. So mass of the sphere is constant and the surface area of the sphere is constant, as I already told you, and this would be multiplied by 2 pi r square sine theta d theta, right? And r square would be cancelled out, pi would be cancelled out, 2 will cancel 4 by 2, so this will be m divided by 2 sine theta times d theta. This is the differential mass of the ring. Okay, so we had the earlier figure like this. This was the axis, this was the ring, differential ring, this was the distance x. Now what is the moment of inertia of this differential ring from this axis x? You see, since the distance is x, di would be equal to dm times x square. Okay, so what is dm? Dm was m by 2 sine theta d theta times x. X was r sine theta, so this would be r square sine square theta. Alright, this is di. Okay, so di would be equal to m by 2 r square sine cube theta d theta. Alright, this is the di. This is the differential moment of inertia for the ring. Alright, so di is equal to m r square by 2 sine cube theta d theta, and we can integrate this. This will go from 0 to I, this will go from 0 to pi. Alright, this will go from 0 to pi, this will not go from 0 to 2 pi, because you know the ring only extends to 180-degree angle. You see, this is the ring, alright, and this is the angle theta. The only, you see, to cover whole ring, this angle will go from 0 to 180. That's it. This angle can go from 0 to 180 to cover the whole ring. Alright. So this is from 0 to pi and this is sine cube theta d theta, right? So what is the solution of this? So I is equal to integral 0 to pi m r square by 2 sine cube theta d theta, right? So we can break this sine cube theta. This would be equal to 0 to pi m r square by 2 sine square theta times sine theta d theta. Okay, right. So what is sine square theta? Sine square theta is 1 minus cos square theta times sine theta d theta, and this would be equal to m r square by 2 integration 0 to pi I. And let us assume cos theta to be x. So we differentiate both the sides. We have minus sine theta d theta times dx. This would be equal to dx, right? So we have x and dx. So we have 1 minus x square times dx. And this would be minus mr square by 2. Limits would get changed now. What will be the limits? You see, at theta was from 0 to pi. So when theta is 0, x is equal to 1. And when theta is pi, x equal to minus 1. So we have from 1 to minus 1. Okay. So I is equal to minus mr square by 2 from 1 to minus 1, 1 minus x square times dx. So this would be x minus x cube by 3, 1 to minus 1. And this is minus mr square by 2 I. Since this is an odd function and we can interchange this. This would be x cube by 3 minus x from minus 1 to 1. Okay. Alright. No, actually this is correct. So we put the values over here. We see minus 1 for x, minus 1 and then again minus 1. This is for x, okay. Minus of minus 1 cube and then minus of 1 cube, right? Alright. Minus 1 cube and then minus 1 cube. And this would be by 3, okay. This is by 3. We are doing separately. You see, we are putting limits separately from plus 1 to minus 1 and then minus x cube by 3 from plus 1 to minus 1. Okay. And minus sign is outside mr square by 2. We are putting limits separately. We can do it. Okay. So this would be equal to minus 2 minus. And this would be minus 1 and minus 1. This is minus 2 and this would be plus 2 by 3. Times minus mr square by 2, right? So this would yield 2 comes out and this would be minus 1 plus 1 by 3. This would be minus 2 by 3 and this would be mr square by 2 and this is minus. So 2 gets cancelled, minus gets cancelled. So the final moment of inertia is 2 by 3 mr square. Okay. So the final moment of inertia is 2 by 3 mr square for a hollow sphere. Remember, we are not doing it for a solid sphere. This is for a hollow sphere. Okay. Now we move on to the next problem. Suppose I have to calculate the moment of inertia for a solid sphere. Okay. And about this axis. So what I do is I assume thin spherical shells. Because why? Why have I assumed thin spherical shell? Because we have to express the mass in terms of volume now. Alright. This is why. And the best example of a volume which is very thin, and this is spherical shell only. Alright. So we have to express mass in terms of volume now, because the volume is the only quantity which is constant over here. Volume of this sphere would be equal to m divided 4 by 3 pi r cube. This is the radius of sphere. Okay. So now what is the volume of this shell? I want to know what is the volume of this spherical shell. You see, the volume of a sphere is 4 by 3 pi r cube in general. Okay. Now, in this sphere, there are two concentric spheres. One has a radius r and one has a radius r plus dr. Okay. This is r. So, how do we find the volume? Because volume is entrapped between the two. Okay. And this is so small that this hollowness will not be visible. Okay. Even because, this sphere is not empty. This is a solid sphere. But this spherical shell is so small that hollowness will not be visible, and several of these will make the solid sphere. And this portion contains the volume. Okay. So how do we calculate the volume of this portion? You see, 4 by 3 pi r plus dr whole cube minus 4 by 3 pi r cube. This is the volume of this whole portion. So 4 by 3 pi r plus dr cube, I am expanding right now, r cube plus dr cube plus 3r square dr plus 3r dr square, right, minus 4 by 3 pi r cube, right. So r cube will get cancelled out. Okay. And dr is very small, so we neglect it at 0. Dr square is also very small. Since dr is very small, we can only write dr. Dr cube and dr square will be very, very small, so they tend to approach 0. So the only expression I got is this. 3r square dr, 3 gets cancelled out, is 4 pi r square dr. This is the differential volume of this spherical shell. So what is the differential mass of the spherical shell? The mass of sphere divided by the volume of sphere. 4 by 3 pi r cube times 4 pi r square dr. This is the differential mass of this spherical shell. Okay, this is the differential mass of the spherical shell. Now you see, I am redrawing the figure. This was the axis, this was the spherical shell. I want to calculate the differential moment of inertia for this spherical shell. You see, this is the radius r. The spherical shell is at a distance r from the axis x. So di would be equal to dm times r square. Okay, but this is not the moment of inertia. Di will not be equal to dm r square because this is a spherical shell. This is not a ring. Okay, earlier I had assumed ring had a moment of inertia of mr square. Earlier I have derived it, but the spherical shell has a moment of inertia of 2 by 3 mr square. Okay, so this differential moment of inertia would be 2 by 3 times dmr square. This would be the moment of inertia for this spherical shell. All right, now we can proceed. You see, 3m by 4 pi r cube times 4 pi r square dr. This is the differential mass, and 2 by 3 times differential mass times r square. This would lead to 2 by 3 times r square. This would be equal to di, differential moment of inertia. Okay, 4 pi gets cancelled out, 3 gets cancelled out. So we have 2m by r cube times r4 dr. And obviously r will go from 0 to r, and this di will go from 0 to I. So we have, this would be r5 by 5, 2m by r cube. This would get cancelled out, and I would be equal to 2 over 5 mr square. Now this is for a solid sphere. Okay, you see the difference. Moment of inertias are different for hollow sphere and a solid sphere. Okay, I explained you the difference. Alright, so guys, this was my analysis of moment of inertia. You will find the concept useful for understanding and clearing out your concepts. You will know how to solve a problem next time a complex problem comes. So the next video will be of previous year question relating to these things and the previous videos and the topics of the previous videos which I have taught. Please like, view, review and recommend, and thank you very much.